Good afternoon and welcome to our last session of the day, the Stuart Beal methodology session. My name is Ana Ruiz and my affiliation is Gilead Sciences. Our first speaker today is Freya Bachman. She is completing her PhD in mathematics, passionate about the application of optimal drug dosing for patients to achieve their best possible outcomes. And today, Freya will be presenting further advancements on this particular area of research. Freya?
Hello. So thank you, Anna, for the introduction. It's a great pleasure to be here and present this work. All right. First, what is it all about? We consider a pharmacometrics model for some disease and a dosing schedule for the drug. And our goal is to compute optimal drug doses. That means the doses which are necessary in order to achieve a certain desired response. So, many of you are familiar with the modeling and simulation approach. You simulate many different doses and pick the one that you like the most, such as the one which has a response that is as close as possible to your desired response. And clearly, this has brought lots of improvement to dosing recommendations, but let me suggest to go the other way around. If you know your desired response and you utilize optimization to compute the dose which is necessary in order to achieve this desired response, we call this modeling and optimization, and you might benefit from that in situations when simulations are computationally expensive, for example, or when dose-response relationships are nonlinear, such in that illustration, and in other complex situations, perhaps. Now, some of you were approaching me saying, yeah, well, but what if there are side effects? What if there are unwanted, potentially harmful conditions of the patient that we need to avoid? Then we need to include state constraints in the optimization. State constraints are inequalities separating feasible from infeasible model states. Let me give you an example. We consider a cancer patient undergoing chemotherapy. Our desired response is to reduce the tumor weight, but myelosuppression is a dangerous side effect, a condition that needs to be avoided. So we have two targets, but our priorities are pretty clear. Our top priority is to avoid myelosuppression. This will be characterized by the state constraint. And in addition, we want to reduce the tumor weight as much as possible. Why is this a cool thing to do? Because including state constraints in the optimization allows us to compute optimal drug doses regarding efficacy and safety targets. And there's plenty of examples where this comes in handy. So we already talked about example 1, which is to minimize tumor weight while avoiding myelosuppression, characterized by a state constraint that the neutrophil count should remain above a certain threshold. Now, example 2 is to eradicate bacteria with minimal AUC of the drug. Here, we have an efficacy state constraint because it is our top priority to avoid sepsis, to have the bacterial count below a certain threshold. So, oh no. This is the state constraint, and here we have the state constraint, and these are also other examples, and all of these examples are of the same type. We always minimize something subject to an inequality state constraint. So, this is our original problem. To compute optimal drug doses which minimize an objective function subject to a state constraint, such as to minimize tumor weight W, subject to maintaining a safe neutrophil count N above 1, or equivalently, to have N minus 1 less or equal than 0 at all times t in the observation interval. Here. So this is a very tough problem, trust me. So step 1 is to transform it into something easier, something that we can handle, a classical optimization problem, by adding this penalty function to the objective function. This is the penalty function. So, roughly speaking, the penalty function is 0 if the state constraint is satisfied. Then we minimize the original objective, this here, and everything is fine. However, if the state constraint is violated, the penalty function attains very large values. If n minus 1 is greater than 0, this part will be greater than 0. And in order to make it really hard, we multiply with this large penalty parameter gamma, this guy here. So the sum of the two is very large, and thereby the minimizing algorithm will pick another dose, providing a lower penalty plus objective function value. So this is an indirect way to enforce the state constraint, and it could also be considered an extreme form of weighting the two criteria. All right. Now, you might want to argue that this does not look particularly easy right now, but this is a classical optimization problem. There is no constraint present anymore, and you can solve this on your computer in non-mem, and I'm going to show you how. First, you need to choose a large penalty parameter, such as the gamma is 10,000 in this example, and we fix the shift function mu equal to 1. This is a technical thing that you don't need to worry right now. Then we need to compute these two values, the objective function value and the penalty function value, and we do so by utilizing additional differential equations, such as when computing the IUC, for example. We introduce an artificial state variable, obj. The right-hand side is the tumor weight W. The initial value is 0. And then, by calculus, the objective function value is the value at final time of this artificial state variable. For the penalty function value, we proceed analogously. The right-hand side is just a bit more complicated. All right, now we are ready to compute optimal drug doses which minimize some function, and luckily we already published a paper in January how to do this. So here I will only present to you the key tricks, what to do, and you can read the rest at home. So in the data file, we indicate the dosing time points with amount equal to 1, and we indicate the final time with a dummy observation. In a control file, we fix the model parameters in $pk. We associate the doses with the estimation parameters theta. Then we assign the scale factor f equals theta, because f times IMT is the dose in non-mem. So now non-mem knows that theta is the dose. Then we code the pharmacometrics model and also the additional differential equations to compute the objective function value and the penalty function value in $DES, and assign the output to be the sum of the two in $error. And then we can run the minimization via $EST minus 2LL. All right, let's look at some examples just for the purpose of illustrating this method. Example 1 was what I previously mentioned, like we combined the CAR tumor growth inhibition model with the Friedberg myelosuppression model. Daily dosing starts at day 12, and each dose is applied 4 times. Our goal is to compute optimal drug doses which minimize the tumor weight while maintaining a safe neutrophil count. So, in the right panel, we see the tumor weight. We see the tumor grows untreatedly until day 12, then drug administration starts, and the green area indicates the objective function value. In the middle panel, we see the neutrophils at their baseline of 7. Then drug administration starts and they drop down towards their threshold, but remain above. The penalty function value is close to 0. And in the right panel, you see the optimal doses depicted as little blue crosses and the resulting concentration. The doses are not actually integer values, I rounded them here. And I want to emphasize that any higher doses would provide a smaller tumor, but also result in the neutrophils dropping below their threshold. So this is the smallest the tumor can get, subject to this constraint. Example 2 is a 2-compartment PK/PD model for bacterial eradication. Dosing is twice daily as a 1-hour infusion, and our goal is to compute optimal drug doses that minimize the IUC of the antibiotic drug with an efficacy state constraint. The mean value of the bacterial count B needs to be below the threshold of 100 in the considered time interval from 6 to 24 hours. Here you see the results. The penalty function value is close to 0. The optimal dose is 46. And again, any lower dose would not result in a sufficient bacterial killing. So this is the smallest IUC possible, subject to this constraint. All right, to wrap it up now, what's your job? You need a pharmacometrics model with model parameters characterizing an individual or the typical representative of a population. You need to know your dosing schedule, including the dosing time points, the route of administration, and the repeated applications of each dose. You need to know your efficacy and safety targets, and you need to decide which one is your top priority target that needs to be satisfied. This will be a state constraint which the penalty function takes care of. And you need to decide which one is the as good as possible target. This will be characterized by the objective function. Then you can use non-mem to compute the optimal drug doses regarding efficacy and safety targets, and then check your results. Never trust your computer. All right, this is my thank you slide already. I would have never done all this work by myself, so I want to thank the whole team, Marc, Gilbert, Britta, Gabor from the University Children's Hospital in Basel, and also my supervisor, Johannes. Our collaboration is supported by the Botnar Research Center for Child Health. In addition, thank you very much, Bob, for answering all my non-mem questions and also for the cool t-shirt. I hope you can see it. Here I provided the reference of the paper, How to Compute Optimal Drug Dosing in Non-mem. We are currently writing a follow-up paper to include the state constraints, what I just presented here, including additional little things to pay attention to. So if you have a really cool, clinically relevant and realistic example, please send me an email. Now, thank you for your attention. It was a great pleasure. I am happy to take your questions now.
Thank you, Freya. Any questions?
Thank you very much for the very entertaining talk. It was really good. Well, in classical optimization, your penalty function is probably Lagrange multipliers, and they're estimated somehow. Here you just put it 10 to the power 4. Why 4, not 6, not 12, not 1? Could you hint how I would do it at home if I need to reproduce it?
So, correct. This is part of the augmented Lagrangian algorithm. And usually you would start with a like a much smaller penalty parameter, and then compute the doses. Then you would update the shift function, and you would increase the penalty parameter if necessary, and then you would compute the optimal doses again, and it will be an iteration. And as the penalty parameter tends to infinity, the shift function converges weakly towards the Lagrangian multiplier, which is a measure here in that case. I will put all the details into my PhD thesis, I guess. So here we decided that we already get quite good results if we just pick this one set of parameters and look at the results. Because in that picture I showed you, for example, with the neutrophils, that should remain above 1, there was also the case where they are like 0.99999, but it doesn't matter so much for you, as I think. So, yeah, that was a trial and error, basically. And maybe I need more examples to provide a reasonable suggestion what to try first, for example.
Laura Zweb, Leiden University. I really like your enthusiastic talk, and I also think it's a very clean method that you're using. I was just wondering, because in the first slide you really show multiple constraints and also goals you want to achieve. In what way would you integrate multiple goals? So I guess a constraint you can just add, but to sort of weigh between different goals that you want to achieve, do you have an idea how you would approach that?
Like here, actually it's like one goal and a constraint. So the constraint is like the side condition that really needs to be satisfied, and then there's the additional goal that we want to achieve. So in theory, it's also possible to include several constraints with different penalty parameters. They would have to experiment perhaps a bit more, and also check whether there is a solution at all, or whether these are like constraints that cannot be satisfied at the same time. And for the objective function, you can also like use a sum of two criteria.
Okay, thank you.
Last question.
Hi, Andy Hooker from Uppsala University. Thanks a lot. I'm just wondering, so it sounded like you could either optimize the population typical value or an individual curve to get these doses. And I'm wondering if you would have thought about incorporating population distribution, so you can talk about, say, 95% of the individuals having neutrophils that are within this range, or if you've thought about your model having uncertainty, so you can talk about within some sort of uncertainty distribution of your parameters, which doses would make sense, incorporating both of those types of sort of uncertainty as well as individual deviations.
Yes, so for the first question, so far we simulated a population of individuals and computed their optimal doses, and we can do that because non-mem is so fast. And then we could do a regression analysis on these optimal doses. Like, for example, I simulated 10,000 of patients and then did a look at these doses.
I guess what I mean is, could you optimize a dose so that all of those individuals, given the same dose, you have 95% of them above a certain point?
Not yet, no. But maybe next year. But thank you for the idea, yes. Thank you.
Priya. Our next speaker is Dominic Bram. Dominic is pursuing his PhD at the University's Children's Hospital in Basel, with focus in neuronal ODEs in PK modeling. Dominic will be presenting neuronal ODEs structures based on pharmacokinetic principles. Thank you, Dominic.
Thank you for this introduction. It's really a pleasure to be here and present to you our work about neural ODE structures based on pharmacokinetic principles. Before I start with the presentation, I'd like to thank Uri Nahum, Bernhard Steyert, Johannes Schropp, Mark Pfister, and Gilbert Koch for their support and work in this project. So the aim of this presentation is to give you an insight into neural ordinary differential equations and present you our approach to incorporate pharmacometric principles in this method. But before we can talk about neural ODEs, I will briefly introduce neural networks. A neural network is a flexible function with model parameters, and these model parameters can be optimized, or how it's called in machine learning, they can be trained with training data, which is basically similar to a nonlinear regression. And according to the universal approximation theorem, any function can be approximated with neural networks. So these are really the basics. If you want to know more about neural networks, you should read this very famous book by Goodfellow. So now let's go to neural ODEs. And as the name says, they are closely related to classical ordinary differential equations. Classical ordinary differential equations or differential equations with an explicit function on the right-hand side. And this function is usually mechanism-based. So you have distribution and elimination, for example, in pharmacokinetics. But if you don't know this explicit function, you may want to use a neural ODE, which is also a differential equation, but with a neural network on the right-hand side. And this means the right-hand side is then just approximated with this neural network. So one could say that neural ODEs are a data-driven approach. You heard yesterday already about neural ODEs, so we are not the first group using this method in pharmacometrics. One of the first publications actually was this very nice work from James Liu et al. And they used this common machine learning approach of encoder-decoder, and they nicely fitted pharmacokinetic data. So they brought this machine learning approach into pharmacometrics. But yesterday we heard from Uri Nahum that it's always a good idea to include expert knowledge into your machine learning approach. And this is exactly what we wanted to do. So bring pharmacometrics into the NODEs and the neural networks. But combining these two fields brings us to some challenges. First, in pharmacometrics, the data often comes from multidimensional systems with peripheral compartment or transit compartments in the absorption, but we usually only have observations from one dimension, often the central compartment. So how should the data-driven approach of NODEs handle this? Second, in our measurements, we often have noise. And the NODE must distinguish between what is noise and what is really the underlying dynamics in the data. Then, when we have our model, we usually want to do some simulations, for example, for different doses or different dosing schemes. But neural networks, and with this also neural ODEs, don't extrapolate very well to unseen inputs. And last but not least, we also want to learn something about our data. So we want to get insights into the underlying dynamics. But neural ODEs, as many other machine learning approaches, are considered to be black boxes. So there are already different approaches to solve these challenges, and I will present you how we developed our NODEs in 3 steps. So in the first step, we wanted to get rid of this multidimensionality, and we reduced the classical ODE systems to one-dimensional system. Second, we then could substitute the right-hand side of the ODE with a neural network to get to our neural ODE. And in the end, we leveraged known mechanistic structures and combined them with the NODEs and the neural networks. So let's start with step 1. As I mentioned before, we often have this multidimensionality in pharmacometrics with peripheral compartment, transit compartments, even drug receptor and drug receptor complexes in the TMDD model. But we can reduce these multidimensional systems to one-dimensional systems. And I will show you this on the example of a 2-compartment model. Here you see the classical ODE 2-compartment model with central compartment and peripheral compartment. Now we can solve explicitly the peripheral compartment and use this in the central compartment. And this is just to illustrate how it works. The real function would be too long, but then we get this structure for a one-dimensional 2-compartment model. And here I'd like to highlight 2 things. First, you see in red, we now have an explicit time dependency on the right-hand side of our differential equation. And this is something new when we reduce a multidimensional system to a one-dimensional system. And second, even though I show you here only the 2-compartment model, the same reduction is also possible for other models. And we always get similar structures where we have non-autonomous or time-dependent right-hand sides of the differential equation. With this, we can go now to the step 2, to get our general NODE structure. Again, on the example of the 2-compartment model, where we have these 2 functions, one that is concentration-dependent and one that is time-dependent. And now we can just substitute these functions with neural networks. And we get our one-dimensional neural ODE model. With this, we can fit a large variety of pharmacokinetic data. But if we now want to use this NODE and we fit just data from one single subject, something like that can happen, where the NODE almost perfectly fits the training data. But we all know we have noise in our data, and the actual dynamics look more like the green dotted line. So the NODE learned the noise by heart, and if you would perform simulations with this trained NODE, it would simulate the exact same noise pattern which was observed in this specific subject. We can avoid this by training the NODE on multiple subjects. So the noise gets cancelled out, and the NODE learns the true underlying dynamic. So we have our general NODE structure trained on multiple subjects with dose 1. What happens when we make a simulation for dose 20? And here you see an example why neural networks cannot extrapolate very well. So we get totally unrealistic concentrations, even in the negative concentration range, which is absolutely nonsense. So we have to restrict our simulations because we can train our NODE on a maximum dose and a minimum dose, here on 50 and 1, and we can make simulations for doses in between, for example, for 20. even though the NODE was not trained explicitly on the dose 20. So we have our NODE structure trained on multiple subjects with 2 doses, but we still want to get an insight into the dynamics. And for this, I'd like to introduce the derivative versus concentration plot on the example of a 2-compartment model. You see the classical 2-compartment model, and on the left-hand side, the plot for the concentration in the central compartment in semi-log scale. And now on the right-hand side, you see the derivative, or the right-hand side of the central compartment plotted against the concentration. And you see here the typical biphasic behavior of a 2-compartment model. The nice thing about our approach is now that we can do the exact same thing with our neural networks in the NODE. So we train our NODE on data here from a 2-compartment model, and we plot the derivative against the concentration. And here we see that the NODE did not learn just anything, but it really learned this biphasic behavior of the 2-compartment model. And with this, we can get an insight into what the neural network actually learned. So we have a framework for our NODEs, and now we can apply it. So we can use the exact same model structure and fit data from a 1-compartment model or a 2-compartment model, and even more complex models like a TMDD model. And since the TMDD model is quite interesting, we want to get an insight into what the NODE has learned from this data. So we plot the derivative against the concentration, and we see that there is something different. So this initial drop, which is related to the rapid binding, was not learned by the NODE. And this is because we have, in the beginning of the curve, at the high concentrations, we have not very densely sampled measurements. And we cannot see this drop in the data. And as the neural ODE is a data-driven approach, it cannot learn what it has not seen. But in the other parts, we have enough data, and it learned the linear elimination, the transition, and the terminal elimination phase quite well, even though it does not know anything about TMDD. So now we can go to step 3 and combine this with classical modeling, which is also often referred as scientific machine learning. So here we have the scenario where you have a drug already tested in an intravenous bolus study, and we learned that from classical PK modeling that it's a first-order elimination. Now we want to give this drug orally. So we don't know the absorption, and for this we can use neural networks. So we only describe the part where we have no clue what's happening with neural networks, and the elimination here in green we define explicitly. And as you can see, we have data with a strongly delayed absorption, and the NODE was able to nicely fit this data and even make prediction or simulations in between the training data.
1 minute.
Yes. Perfect. So I will come directly to the take-home messages. So with our approach to incorporate pharmacometric principles in NODEs, we can still automatically learn the dynamics of observed training data. We can get an insights into what the NODE has learned with this derivative versus concentration plots. And we learned that we should avoid overfitting by training on multiple subjects. We cannot extrapolate with NODs, but we can interpolate within the range of 2 training doses, and we can combine the NODs with the pharmacometric models we all know. And with this, I would thank you for your attention and would be open for questions.
Any questions?
Yeah, Gibianski Farm. Could you elaborate why you need the first step? Neural network can perfectly handle multiple input-outputs. Why not to work with like a matrix form? Why you need to one-dimensional system?
Yeah, I mean, we have only observations from one dimension, and there are different approaches where you have hidden states in the NODE. We decided to go with this one-dimensional approach to are able to get more insights into the NODE. And we are currently elaborating or looking how we can even get more insights into what the NODE has learned. And this one-dimensionality makes it quite easy to get an insight.
Hi, can you hear me? All good? Right. So, what do you expect now that you do reduce the dimensionality of your system, and you're not really retaining history any longer as it's being propagated throughout a system of differential equation? What happens when you add multiple dosing?
That's an excellent question. We are currently working on multiple dosing. You need to give more information to the neural network. So not only time since last dose, but maybe even time since the last dose. So the NODE knows where in the whole process it was and what happens in the whole system.
Thank you.
Cool. Alexander Janssen, Amsterdam UMC. Thank you for the great presentation, Dominic. I was just wondering, where do you see this going? Do you think this could be like a first step in the modeling process where you like, for example, look at the derivatives and then check from, oh, maybe I should use a two-compartment model? Or would you say, let's get some covariates into this as well and just use neural ODs from now on?
I think both is possible and also good ways to go. NeuNet, or the whole NOD structure, is certainly a good way to screen, for example, for large numbers of covariates and see what covariate has an influence on the dynamics, even if you have like a lot of biomarkers, SNPs, and so on. But also the other way is something, I think there is a poster where they tried to describe then the derivatives basically and try to get from what the NOD has learned to the compartmental model. I think in the future there will be something like, both methods combined.
Thank you.
And just one more question.
Wojciech Ryzanski, University of Buffalo. So going back to this dimensionality question, maybe more general one, this might be about neural networks, not just ordinary differential equations. So we have input and we have output, and then the way we listen to all those presentations, do neural networks allow multi-dimensional inputs and multi-dimensional outputs? And if they do, would that be somehow explored towards not, reducing the dimension of ordinary differential equations that you have shown us?
Yes, neural networks can have multi-dimensional input and output, and this is one solution to solve this, that you have only observations from one state, but you have multi-dimensional systems where you don't know exactly, do I have peripheral compartments, how many peripheral compartments do I have? This is one solution that is tried. But I think this solution brings other difficulties with it. And I don't want to say, or I cannot say one way is right, one is wrong. I think we are at a really early stage of this whole neural ODE thing in pharmacometrics, and we have to see what's possible, what's not possible, which way should we go, and which way is like a dead end.
Thank you.
Thank you.
Thank you.
Our last speaker is Thong Huai Huang. She is currently pursuing her PhD at University College of London with focus on her presentation on a novel automated POP-PK modeling methods comparing the performance of several algorithms developed in the R environment.
Thank you, Anna. Thank you for your nice introduction. And thanks for this opportunity to present my work on automated pharmacokinetic modeling. So today, I'm going to introduce my work, and I will go through the methods in this study and what we observe from the results, and ending with the conclusion. So firstly, the story starts with building a nonlinear mixed effect model. So as we know, this process is not easy. So we need to face a series of questions when building a model. So for modelers like me, you can see the little cute human here. So we use sequential methods to test the model components step by step. And usually we identify the local optimal solutions at each stage. So usually there's no backtracking, which means when it comes to the covariate model, we don't often check the basic model structure at that stage. But years ago, Jonathan Wade told us actually different model components are interrelated. So this made me realize that maybe this stepwise strategy might not be the optimal. So efforts have been done to look at a different modeling strategy, for example, genetic algorithm. So in this algorithm is improved models iteratively and after some iterations, and it can help to guide to the best solution. But as we know, evolution is long, so we continue to think about trying to borrow the other idea from the nature. So thanks for the nature support. There's another available algorithm called ant colony optimization. So it is inspired from the ant foraging behaviors. So in the nature, the ants use collective intelligence to find the shortest path to the food by following the pheromone trail they deposit on the path. As you can see here, the right pheromone trail. And the shorter path and the stronger pheromone trail. So finally, these strongest pheromone trail can guide the ant to the best solution. So to our knowledge, actually, this algorithm hasn't been used in POP-PK analysis. So therefore, we think about to construct such diagram, example, ACO path for POP-PK analysis. And then the ant can conduct practice with precision building models. And from the positive feedback from the model performance, it can help us to lead to the best solution. So we are really interested in the algorithm performance I mentioned before. So currently, to our knowledge, there are limited range of the models are tested for designed algorithms. And then it is really common to compare the designed algorithm with human being modeling just by the better fit. Sometimes it could be the lower AIC, BIC, or V. Sometimes it could be the information criterion with introducing penalty rules on atoms. But it is not usually done to fit all possible models. So in other words, exhaustive approach, to find the true best model in the search space given the data. So in this study, our overall aim is to evaluate the automated algorithms for selecting the true best model identified by exhaustive search. And this will be addressed by 4 objectives. So the first one is to generate the simulated data set. There are 72 cases. And secondly, we will fit all of the positive models by exhaustive algorithm. And it's also very important to explore appropriate fitness functions for designed algorithms. And then we can conduct the algorithms and compare the algorithm performance. So all of the modeling work is done in Enomics R2, open source R package. So after introducing the background information, I will introduce the methods how we achieve about objectives. So first, it is the design of the search space for all of the algorithms. In this study, there are 8 model components in the search space, so which are the number of the components, different random effects on parameters, and the 3 types of the residual error models. After design the search space, so it's come to the simulated dataset design. In this study, there are 72 simulated dataset cases, and there are 3 data types, the rich data, sparse data, optional design data. And I expand the rich data here, and you can see it includes the 1, 2, 3 compartment model and different combinations of random effects and the 3 types of the residual error model. So after we design the simulated dataset, it's come to the fitness function exploration. So it is divided into 3 steps. Step 1 to generate the simulated dataset by optimal design. And for the step 2 to conduct the parameter estimation by exhaustive algorithm. And the third one, we will evaluate the different criteria. So we will have a look at whether these criteria can help exhaustive algorithm recover the original models. So after the exploration of the fitness function, so it comes to the algorithm development. Firstly, I will show you 3 workflow of the algorithms. The first one is the exhaustive algorithm. So it is easy to understand that we will test all of the candidate models in the search space. And for stepwise algorithm, so the sequential order is from the structure to IV and to RV model. And for the last one, genetic algorithm, it includes the basic elements of the GA, for example, model selection, model crossover, model mutation, and there are also local search in GA. And after iterations, it can help get to the best model solution. And then it's come to the important part, ACO design in the POP-PK modeling. So in this study, the first step for ACO design is to construct the solution path. So as I showed just now, the ants can try different paths, and which represents building the models. And then after the practice, we can get the model results and evaluate the models and get the positive feedback from the practice. So at the beginning, we also need to initialize the pheromone. So as you can see here, each model component shares the same pheromone contents, and which means at the beginning, they share the same probability to be selected. And then it starts the traveling. So I want to conduct the practice. So I show 2 diagrams here, so which represent the 1 compartment model and the 2 compartment model. And after conduct the practice, we can calculate, based on the model results, we can calculate the pheromone. So pheromone calculation is based on the ranking of the fitness function explored in the previous section. And on the other hand, in the ACO system, there's a pheromone evaporation part, so which means there will be a constant of the pheromone loss. So after we calculate the pheromone, and the ant can start a new travel based on the probability for each model component. So the probability of each path was calculated based on the ratio of the pheromone deposited on that path to the total pheromone present on the path. So I showed the general workflow of the simple ACO here. So it includes the 3 steps: initialization, parameter estimation, pheromone update. So after we design all of the algorithms, so we would like to see the performance of the design algorithm. So we use the accuracy rate as the measurement, so which defined as the percentage of the models selected by the design algorithms that match the true best model identified by exhaustive algorithm. So after I introduce the methods how we achieve that, and then it comes to the results part. So the first result we get is about the fitness function exploration. So what we observe is actually if we just consider AIC, BAC, OFE and the criteria, actually the exotic algorithms, cannot recover the original model. So which means the original models are usually not the best model selected by exotic search. And we try to introduce the penalty rules on some atoms like RC shrinkage, variance of the residual error model. So what we found that is, firstly, when the penalty constant reaches to the 10,000, all of the models selected by exotic algorithms are high quality models. And the retrieval rate of the simulated models by exotic algorithms also reached the highest value with the overall retrieval rate 71%. So we use this equation as the fitness function for all of the designed algorithm. And then it's come to the algorithm modeling process. I will show you the designed R-Shiny app to see the procedure. So this is the overview of the designed R-Shiny app. And we just need one click to input the data set and another one click to run the model, run the algorithms, so we can get the details of the modeling work. Here I showed the stepwise algorithm output, so we can see, each iteration's result, and it can help us to select best model ultimately. And for genetic algorithm, it is available to see the fitness plot for each model and each generation. For ACO, it is similarly to see the fitness plot. Besides the fitness plot, for ACO, it is also available to see the pheromone update for each iteration. Of course, for each model performance, it will be right down in the table shown here. So finally, we conduct the experiments for the 72 simulated cases by using the final parameter setting here. Finally, what we observed for the algorithm performance is for different data types, actually, they have the different performance. For optimal design data, what we observe is GA and ACO have the higher accuracy rate than the stepwise algorithm. And similarly, for rich data, the GA and the ACO have the higher accuracy rate. But when it comes to the sparse data, what we observe is actually GA has the lowest accuracy rate than the other two. And among these three, ACO has the highest accuracy rate. So what we conclude from this study is, for the first thing, for fitness function exploration, it is very important to consider the RC shrinkage and the variance of residual error model as the penalty. And in our design case, 10,000 penalty was appropriate, but maybe it is needed to revise when extending to other PK scenarios. And for algorithm performance, what we observe is for optimal design data, race data, ACO and the GA show the similar performance, but both of them outperform the stepwise algorithm. For smart data, ACO is superior to the GA and the stepwise, so which means ACO could be potentially automated modeling algorithms. So it is just the start of the story, not end of story. So there are serious considerations in the future. For example, in our current studies, it's just a single dose with the intravenous administration. But we will think about other rules of the administration or other PK scenarios. Of course, the sighting initial estimate is really important. In the future, we will apply them to the real-world data, not simulated data. And I really appreciate all of the people who contribute to the project, and thanks for the founder. Thanks for your attention, and really a pleasure to answer your questions. Thank you.
Rob Bees, University at Buffalo. Really fascinating approach with the end colony optimization. So I had a question. So as the paths get more complex, how tractable are defining the paths going to be if you have many options. You had an exhaustive search here of 72 and some limited sort of decision points in terms of that pheromone matrix. But if that expands to be 10,000, 50,000 kind of sort of options for that, how do you implement this with respect to path definition?
Sorry, if I understand correctly, you mean how I design the attraction of the path, each path, and the two.
Yes, if you get a more complex set. So you had an exhaustive search space of 72 models, if I understood correctly, or 72 possibilities. But what if your set is closer to it goes into the tens of thousands or millions in terms of these possible decisions? And well, actually, that's the first part of the question, but.
Okay, so in our search space, actually there are 243 models, possibilities,
Okay.
and the 72 are simulated data set. We create the 72 PK scenarios. So we use the algorithms to test each scenarios to see whether the algorithms can select the same model, compare with the exotic search, because we make assumption the exotic search give the correct answers. So yeah, hope this answers your question.
It does. And in terms of defining the paths, you mentioned, you cited, of course, Janet Wade and Stuart Beal's paper, and the idea of directionality or movement. But does the path constrain the order of decisions?
Actually, in this study, we use the best model in the history as the answer model, so not the final model converged. So I think you mean for ACO-RGA, finally they will converge a model and whether that model is the answer. So actually we use the history best model as the answer for the algorithms design.
All right.
Is that your answer?
No, I was just curious about the direction in terms of decisions going sort of back and forth in terms of elements included or not included, or is that intrinsic in the pheromone matrix that evolves?
You mean how I calculate the probability, like the pheromone, how I measurement the pheromone for the ACO? Does I understand correct? So maybe I can explain that.
Maybe we should probably, this is going to be probably a more detailed discussion, but really wonderful. Thank you.
Yeah.
Enjoyed the presentation.
Yeah, thank you. Thank you for your question.
Hi, Andy Hooker from Uppsala University. Thanks a lot. It was very interesting. I was just wondering about these nature-based heuristic optimization algorithms, and you chose to use the ant colony optimization, and there's the one I'm most familiar with is particle swarm optimization. And I'm wondering if you know about the comparisons between these different methods and maybe why you chose ACO over PSO?
Yeah, thanks for your question. It's really a next question. Yeah, actually, there are many heuristic algorithms like PSO. So the reason why I choose the ACO first is the ACO algorithm is really close to the human being thinking. For example, ACO is to try to allocate the probability on the model components itself. But for PSO, to my own knowledge, PSO and the GA, they try to allocate the probability on the whole model. And so it's different with the human thinking. And another reason we choose ACO is quite flexible to revise for the target question. So it's, for example, for GA, usually we use the binary code for the solution. But in the POP-PK analysis, sometimes there are some 3 options for the same component or 5 options for the same component. So in this case, maybe ACO is more flexible. And sometimes the model components are correlated. For example, if it's one compartment model, we can't consider whether we should introduce random effects on the peripheral compartment. So ACO can, by ACO path design, it can deal with this problem. So that's the motivation why we use ACO first.
Thanks.
Yeah.
Last question.
Thanks for the presentation. Yeah. Martin Bergstern from Prometheus. So is there a risk with these approaches that we are developing unnecessarily complex models? This approach aims to develop the best possible model. I'm quite often satisfied with just a good model.
Yeah, I mean, thanks for your question. It's a really good question. It's really hard. I mean, to differentiate the best model and the good model. Sometimes they have really similar parameter estimation, but I mean, from this study itself, go back this study itself. So what we want to know is whether, these optimization algorithms can help us to achieve the target. So currently the target is to find the best model, but if we change the target to good model, we can define so what the good model is. Maybe we don't use such strict penalty rules. Maybe we can think about the parameter estimation. But what we want to know from this study is whether the algorithms can help us to find best model. But of course, as I mentioned, I think it is also available to see whether it can help us select, filter some good models. So whether, some good model is enough for us to, for the application or clinical trial or something. Yeah, hope it's helpful. Thank you.
Thank you.
Yeah.
So before we close the session, one housekeeping item. Tonight is a social event, and I just want to mention that everybody that registered to this meeting is invited, and we will wait for all of you at 8:30 at the NH Hotel. Thank you.